So in the previous videos, we have looked at how we apply the complex numbers in solving electronic circuits problem, especially in looking at the impedances for different RL or RLC circuits. So in this video, I thought it will be very nice, if we put some values into this and we try to apply this to look at, for example, the voltage or the current or in a given circuits. So let's look at the examples that I have choose. So essentially I have only used one example and these numbers are arbitrary. So here I have RL in the series circuit where the resistance is 10 ohm, and you have an inductor which is a coil with inductance of 2 Henry and the input voltage with a magnitude of 20 volt and an angular frequency of 5 radian per second. So with all this information, we want to find the amplitude of the current through the circuit. And we know that since this is a series, the current that goes through the resistor and the inductor is going to be the same. Right, so how do we solve this? So the first thing we need to do is to recognize that the input voltage is going to be a sine or cosine wave, and this can be written in the complex form as V equals to V naught E I omega t. Right, so the V naught here is the magnitude and this is 20 volt, and omega is the angular frequency. So omega itself is equals to 2 pi f. So you have to be very careful because you have to see whether is it a frequency or angular frequency that you are talking about. And t here is time, so you have t going from 0 up to whatever numbers that you want to consider. Then the next thing will be to look at the impedance of the circuit. And in the previous lecture, we have looked at the impedance of RL in series circuit, and this is given as Z equals to R plus I omega L. So again, this is in the complex form. So in order to find the amplitude of the current, it is sufficient if you put the time t is equals to 0. So when t is equals to 0, you will realize that the ei omega t is going to be equals to 1. So then you have v naught equals to 0, and you have v naught equals to z I naught, right? So on both sides of the equation, the exponential term is going to be equals to 1, and you have this simple equation. So now what you want to find essentially is going to be the I naught. So you know what is Z, you know what is V naught, and you can use it to find I naught. Right, so here I naught is just simply V naught, which is 20 divided by R plus I omega L. Then this is the complex number, and we have done this exercise many times. We have 1 over a complex number, and you just have to do a simple complex algebra, and you will get I naught. So I will leave this as an exercise to you, and I will go on to show you how is the wave going to look like by using the Octave software. So now we want to plot the voltage and the current in the RL series circuits. So the first thing before we do any plots is to define the parameters. So one of them is the resistance, which is 10 ohm. We have the inductance given by the equation, which is 2 Henry, and we have our angular frequency omega equals to 5. The magnitude of the voltage is 20. And finally we need to define the t, which is, let's take it as a linear space between 0 to 2 pi, and that's it for the parameters. And now we can start to calculate the impedance. So we know the impedance in this case, since R and L is in the series circuit, the complex impedance is given by R plus I omega L. And this is how I put it into the Octave. So you have a complex and then you put in the x and y component of the complex number, which is the R, and on the other hand is omega times L. So now we can actually calculate the voltage as a function of t time, and let's write this as v naught times exponential I times omega times t. So now we have this, and with the Z and V available, now we can calculate the current going through the circuit. That is, now I is equals to V divided by the impedance, right? So now let's now everything we have all things ready. We can plot this. So let's plot the voltage as a function of time, and we put this with a symbol O over here and here. So this is the plot of the voltage as a function of t on the x-axis, and we want to now put in the current as a function of time. So let's put I plot ti, and we use a different symbol for the current. And now let's look at the so I need to put the command hold on so that we keep the plot for the voltage, and then I plot the current on top of it. So here you see two plots. The one in the blue line here, this is the input voltage, and the one which is given in the orange color here with a smaller amplitude, this is the current, right? So here you see that the current is shifted with respect to the voltage by a certain phase. So now in the next part, what we want to do is to calculate what is the phase shift between the voltage and the input, right? So we want to look at another plot first. That is, we want to plot the voltage. The next thing we should do now is to actually look at the magnitude of the current going through the circuit, which is what the equation asks for. So here now you have the I, which is the current, and the only thing you need to do is to find the absolute value of the current I, and this is going to be equals to 1.4142, right? So this is the magnitude. Basically, this is the magnitude of the current. So if you want to double check, what you can do is you can define a new variable here, I new, which is new current, and I use 1.4142, which is the absolute value of the current which we have calculated just now, and then we multiply by exponential I times omega times t, and then we will plot this. So let's plot I new now, and we should probably use something else to represent this I new. Now let's look at the so here you see that that this is the one given in slightly on the lighter end of orange, I would say. So here you have another line, and you see that the amplitude is correct. In here, basically you're comparing the I new which you have just calculated and the I which you obtained by using the equation V divided by Z, and you see the amplitude is the same, but now the difference is the phase shift. So again, we have to define what is the phase shift in this case. Okay, so let's just close this, and we will go next to the how to calculate the phase shift. So to calculate the phase shift, you can actually find the equation in any electronics textbooks. The phase shift is defined in this case since we do not have any capacitor. So the phase shift is equals to the arctangent of the omega L divided by R. So here the phase shift is equals to 0.78540, and now let's just plot again the input voltage, right, like this. And now we want to hold on to this plot, and next we want to what we want to do is to plot the current as we have calculated it, and then we want to shift this current by an amount given by the value of phase over here. So 0.7840, sorry. And then we will see that in this case, after you have shift the current by this amount of phase shift, you will see that the current and the voltage are in phase. So as you have seen just now, the current and the voltage are out of phase by this amount of difference, right? So now let's plot the current which we have calculated earlier by this. So let's just look at it again. So this is it, but this is kind of too small for us to see. So let's just close this, and what we do is we are going to plot V, and we will hold on to this plot again, and then we will plot the current, but let's increase the magnitude of it by 5. Okay, and now we are going to calculate the I new. So let's call I new now to be equals to I, but then we are going to shift this by an amount of I phase, and now we are going to plot T I new, and the 5 is basically just to increase the magnitude of this current. Okay, so let me just increase the size a little bit, and then here you see the one in the blue color. This is the input voltage. The one that is in the dark orange color, this is the current that you obtain using the I equals to V divided by the impedance Z. So you have this this current which is shifted by a phase difference with respect to the voltage. And now the lighter orange or yellow here, this is the current that has been shifted by a phase difference of 0.7854, which we have calculated earlier. And here you see that this is in phase with the voltage, right? So here you have here the easy way is to look at the y-axis equals to 0 over here. So the blue line and the lighter orange line here, they reach 0 at the same points, as you can check here for all the points here. Okay, so now so basically this is just to show you what is the meaning of phase difference, right? So basically the phase difference is the difference in the phase of the voltage and the current in the RL series here. And also just to give you an idea of how to plot the voltage and current using Octave. So that's it. So thank you very much.